just trying to get the artwork done here because both the problems I'm going to show you this morning, they're not as easy to draw as you might think. So that's the first one we're going to take a look at there. We'll come back to that in just a minute, and then I'm going to get the second one up here so we can just keep continuity going. Good morning, everybody. So, we're going to finish up our conversation today. All the stuff we're going to cover in the course, we're going to bring it in for a landing today, where they look at finishing up a little bit of 3D stuff. But before we get there, you all have had now a couple of days to see the final exam, and I want to talk to you about that. I want to field questions that you might have about that. One thing I do want to, before I forget this, folks, and I mentioned this to you when we were together last Thursday, I just want to make sure for anybody in the room who is working with me to address issues with the midterm exam, and there's a number of you here, we've already talked, make sure and stop by before you leave here today, just to make sure. I got a list with everybody who's here. I just want to make sure I've got your name correct on the list, so I make sure and give you credit for that, versus I don't give you credit because I didn't have your name on the list. So just make sure and I put a check mark by your name. That's all I'm asking you to do, folks. And that is, again, to ensure that we have been talking together, that we have talked after your midterm, so there's no ambiguity as to what the plan was to remedy that. So make sure and do that. Sorry, this folks was something in the old eyeball there. What questions, let's start things off. What questions might you have right now on anything having to do with the final exam? And that, of course, is open to any of the problems, folks. Does anybody have anything at all? Any questions? Yeah, fire right away. Go ahead.
For problem number 2,
yeah.
it says that the force after the equalize the reaction force not maintained. Does that mean the force at over B has to equal the force at B?
Yes, exactly right. I'm going to repeat that so I make sure everybody hears it, okay? So the question that was posed right here, and it has to do with problem 2, which that's the distributed load problem, right?
Yep.
So the problem statement tells us we're trying to figure out what the magnitude of that force is going to be out there on the end of that would be needed to equalize the reaction forces, right? To your very good point. Everybody hear me when I say this. The way that you're going to do that is to set those two forces equal, in the sense that don't call one of them some variable name and another one some different variable name. Give them the same name so that you're solving for that one variable, right? The one variable in the equations. That's the exact way to do that. Yeah, great question. What other great questions do you guys have this morning? Look it over. Yeah, Nate, I gotta come hear you. Problem 2? Yeah, sure. Let's just, without going into tremendous detail. So the question is well, how do we do problem 2? Let me just kind of give you a rough look at what that looks like up on the board here. And again, folks, you need to know I don't have it committed to memory what that problem looked like, so I don't remember. I can look at it and be a little more precise, but I don't think I'm going to need to. We've got a pin in a roller somewhere. There's a distributed load, whatever that looks like, and again, I don't recall if there's some triangular elements to that. I think there is. But whatever, there's a distributed load, and then if I remember right, I'm asking about some sort of a force that's sitting out here. Am I right so far? Yeah. Okay, good. So how would we work this problem, right? So I want to answer that from the perspective of what am I looking for? The first thing I'm looking for is your understanding of how to convert the distributed load over to its equivalent point loads, all right? So Nate, to your question, the first thing I'm going to want to see from everybody is, did you convert this into its equivalent point loads? And if there's a couple of elements, then that's fine. You're going to have one for a rectangular piece, one for a triangle piece, whatever. But then this all goes away, right? So when we've converted the distributed load, then the distributed load is literally replaced with point force equivalents, right? Now, that's the primary thing I'm going to be looking for. Now, at this point, this is just like any other problem, right? At that point, it's like any other problem. At that point, we're looking at this saying, okay, pin, pin equals, my gosh, this pen's dry. Let me see if I can find a better one here, folks, because otherwise it's going to suck. So pin equals some potential Y force, some potential X force. Roller equals some potential Y force, right? We all know that. So at this point, call them whatever you want to. Now this is pin A. Call it AX. I mean, that's what we usually do. The takeaway from the previous question, though, was what do we call this and what do we call this? If the goal is to make these two forces be equivalent to each other, give them the same name. So, I don't know, call it whatever you want. Call it AB and call it AB. I don't care. They got to be named the same. And then at this point, it's equations of equilibrium. We're going to write 3 equations of equilibrium. One equation is going to tell us right off the bat, that thing goes away. But then the final 2 equations are going to tell us what these forces have to be, or what these forces are going to be, and what this is going to be. If you think about this, at this point in time, we'll have 2 unknowns, because AB is an unknown and F is an unknown. 2 unknowns, 2 equations. The equations of equilibrium take us there. So, Nate, to answer your question further, and put it kind of in a short bullet point thing, right? I'm looking for 2 things. Did you know how to deal with a distributed load? And after that, did you just treat this like any other problem and just trust the process? Free body diagram, equations of equilibrium, done. That's it. Does that take care of you? Sweet, yeah, no problem at all. Keep them coming, folks. The more you ask, the better it is. What other questions might you have? Yeah?
I got a little stuck on problem 3. So we're only given the coefficient of friction.
Yes.
On that one. Set up the free body diagram correctly. Set up my the equations, but I'm not really sure I'm not sure what the path is here, I guess.
Okay, so let me just ask a couple high-level questions, okay? So you got a free body diagram right now. The free body diagram shows the, and remind me, that's asking for what? The maximum angle theta, is that correct?
Yes.
Okay, so I got a free body diagram showing a box tilted, right?
Yes.
There's going to be a weight force on that, and a normal force and a frictional force, right? Or however you draw that. In your free body diagram, I don't know, I need to see it. Does somebody have a hard copy of this I can take a look at?
I got a drawing.
That'll work. Oh, thank you. I'll just work with this one. Appreciate it, Junior. So, without giving the whole problem away, right? I wanted to start with this. Folks, if we're just, and remember I said this is a problem that may bother some of us because it's really simple. If we look at this problem right here, we've got, oh, and I forgot to add in the angle on that. So the angle is the thing we're looking for, right? So there's theta here, which means if we choose to use an axis system like this, then that angle theta is right here. Right now, if we were to write, just based on that free body diagram alone, if we write the equations of equilibrium, you're going to find that the weights are going to cancel out, and you're left with 2 equations. One's going to have a cosine theta, and one's going to have a sine theta in it. And remember, the identity sine theta divided by cosine theta is the tangent of theta. And so this is a trust the process, okay? That's your free body. Trust the process of writing the equations of equilibrium, and you're going to find that you're going to have a term with a sine theta in it, a term with a cosine theta in it, the W's are gonna cancel, and that's gonna give you enough information to figure out what theta is. Does that help? So like I say, I don't know how much I can go further without just saying, yeah, here's how you solve the problem. So if that helps, good. Okay, what other questions do you have? Keep it coming, folks. We've looked at problem 2 now, we've looked at problem 3 now. I remember what's problem 1. Oh, it's centroid problem. Okay, so that should be pretty straightforward. Are there any other questions at all, anybody? Going once, going twice? Okay, if no other questions, let me say one last thing about problem. So we talked about problem 3, we talked about problem 2. I just want to remind you that what I'm going to be looking for on problem 1 is, did you follow the plan? Write the centroid table out, properly fill it in. Junior, do you mind if I take a quick look at that one more time? I just want to look at it and see if there's anything. Oh yeah. To remember, folks, as this problem says, at that center there of the circle, we've got a semicircle sitting on top of that, right? The only thing that's new here that you've not seen before is the formula for the centroid of a semicircle. And I can tell you right now, if you haven't already looked it up, the centroid of that semicircle has to sit, as all centroids must, sit on the axis of symmetry, right? And the distance from the flat edge up to that centroid is 4 times the radius divided by 3 pi. So if you haven't looked it up, look it up. That's what it is, all right? So with that, you should be able to figure out centroid location of that. Honestly, folks, I think this is just a very straightforward, if you know how to fill in the table, if you followed the guidance on how to do that, I think you're gonna have no trouble with this problem at all. And again, I'll go one more time. Did anybody have any questions about problem 1? Yeah, fire away.
When you're dividing up everything, I did the top half of just like the cap, that's what we call the cap. I did the top half of the cap, the area of that, so it was the full area of the first semicircle, and I subtracted the bottom area, which was of the other circle. And I did the bottom. Is that how you think I should approach the problem, or is there probably a better way?
Oh, I want to be real careful about that. Let me generally borrow that one. You might as well just give it to me. Sure. Thanks, man. Appreciate it. I hear what you're saying, and all I want to say about that is what you just described to me is a totally legit way to do it. Totally legit. I look at that and I see a big rectangle on the bottom. I see a little rectangle sitting on top of that starts that tab. I see a semicircle there, and I see a circle cut out of the whole mess. I also see one big rectangle that has its top edge passing through that center minus a smaller rectangle with a semicircle sitting on top of it. Those are all totally legit ways to do it. The one way that I would say, man, don't do that, would be like, hey, I've got this one big rectangle, and above that semicircle, I'm cutting out this like weird arc thing, because I'm telling you, I don't even know where I get the centroid for that piece, but I don't think anybody's going to make that mistake. So, does that take care of you?
Yes, thank you.
Yeah, no problem at all. What other questions, anybody? Yeah, Ginger. Ginger's question has to do with the truss problem. And the roller in that problem looks a little bit odd because what we're seeing is 3 rollers with this piece going through it, and it kind of can look like a roller and a pin, right? I would refer you all back to your notes from our lecture on chapter 3, where on the board here, I drew out different variants of pins and said these are all the same, right? It's a pin, right? But yeah, look that up. You'll see that. It's presented to us in chapter 3 that's just straight up a pin. Oh, I'm sorry, Ginger, I said that wrong. I'm saying you straight up a pin, right? It's straight up a roller. It's all it is. It is a roller. Clarify that. Oh my gosh. The Alzheimer's is getting bad, folks. So does that clear it up for you, or did I just make it murkier? Okay, fine. Go ahead, you go right ahead.
So it's the same thing for problem two, well, it's just wrong, okay.
Let me see problem two. Let's see what you got for problem two. Yes, yes, exactly. You are looking at a pin and a roller there as well. Yep, good question. You guys got to realize all these questions are doing nothing but helping you all out. So does anybody have any other questions you have? Any comments about it? Are we all clear on the timeline for delivery? It's got to be in by no later than noon. Yeah, noon, not this. Is it this upcoming Saturday now? I'm losing track. So you guys are in your final week right now, is that it?
Yeah.
Nice place to be, isn't it? Okay, so yeah, noon by then. I just you guys know, I got one person 3:30 already turned in, so that's good to hear. So it's a good thing. Okay, I don't think I have anything else. And don't forget, it'll be an email submission, PDF, or images, whatever. As long as it's something I can download and see it, that's the only thing. And I got to be able to read it. Hey, one thing I will say, folks, is this. At midterm level, if you're submitting something that I can't read because, let's just face it, it's not legible or not drawn well, I can work with you to get clarification on that. I can't do that with the final. So make sure that what you submit is clearly drawn, clearly stated, all that kind of stuff. Otherwise, it's frustrating if I don't know exactly what you're telling me, and I don't have a great way to fix that. And then the last thing I'll say, only because it's a thing that comes up from time to time, I have had people say, I'm not sure how to solve this, so I solved it one way and I solved it the other way. They're wrong automatically. There's no way imaginable to say, well, I'll accept this one because you were right there and you were wrong. It means you didn't know how to do it. So it's automatically wrong, even though you may have done it right. So don't do that. You have one answer only. Or one solution, I should say, one solution only. Okay, anything else, anybody? All good. Okay, real fine. Let's check out these problems here. So let's focus on the one over here on the far right side from your view. You have there a problem we're going to take a look at as a 3D example of how we are going to do a moment problem. Let me read you the narrative on this problem, then we'll see what we're up to. So, the turnbuckle. The turnbuckle being this piece right here inside this cable. You know, we've probably all seen turnbuckles threaded, tighten them down, cables get tightened, that kind of thing. The turnbuckle is tightened until the tension in cable AB is 1.2 kilonewtons. Ask on this one, simple. Calculate the magnitude of the moment about point O of the force acting on point A. So folks, look at this. We've got this column-like structure right here with this thing hanging off the end. And by the way, folks, as I said doing this, it's just not fun at all drawing these things up here on the board. As I step back and look at this right now, this piece right here should be kind of angled down so it's going right along the x-axis here, folks. It kind of looks like it's back behind the x-axis. It's not meant to be that way. So just make sure we're on the same page with that. But there's this piece emanating off of the column right here. We've got a cable attached here at A, going down to this point down here, ostensibly on the base of this at point B. The turnbuckle has been tightened up here so that it's drawing a 1.2 kilonewton, obviously in tension, force here, folks. And that force, if you could imagine this thing hanging out of the board, so imagine this is something hanging out the board, coming and pointing off at you. There's a cable down here that's pulling it. We know that's going to try to create some rotation about point O. We all know that's what forces do, right? Or, forces and moments do. The question is, how do we calculate that? So here in 3D world, we've already seen that the answer to how to calculate 3D moments is to use the vector cross product, where the moment is going to be equal to some directional vector r crossed with the force vector F. So we know that's our target. All we need to do now is figure out, well, what do those pieces look like. So let's start things off with the force in the cable. Now, folks, the force in the cable, and this goes back to just imagining, and who cares if it's in 3D, right? Things just don't change. If we were to take any piece of this cable here, any piece of this cable, and do a free body diagram of that piece, we know the cable's got to be in tension, right? We've known that from minute number 1. So if I did a little chunk of this cable, which I'm going to quickly draw up here, and I got a little piece of this cable here, then if it's in tension, then I got a force coming off like that, got a force coming off like that, I don't know, whatever we want to call it, let's call it force AB, force AB. It's in tension, right? All right, we also know equals and opposites. So that means that the force that's in this cable, if we want to look at the force in the cable coming from point A, if I separate these two things out and I want to show my force on that cable, then as we've talked about throughout the course, same old, nothing's new here. Then if FAB is pointing upwards here, then FAB has got to be pointing downward here. And now that becomes the force that we want to understand and articulate in terms of a vector. So let's put the vector notation over the top of that. FAB, FAB, FAB. This is the force that we want to articulate as a vector force. We're going to use that in our R cross F mathematics. To do that, there's a couple of different ways we can do it. It really just boils down to something simple, folks. We need to be able to take the magnitude of that force, which we already know. We were told the magnitude is 1.2 kilonewtons. We know that much. But we need to apply that magnitude along a directional vector, the directional vector being the vector that describes the direction of this cable in our 3D space, in this X, Y, Z coordinate system. And there's a couple of really good ways to do that, folks, but let me just show you the one that I just always go to. This is my way of doing it. So the force vector AB is going to be equal to its magnitude F, which again, before we go any further, let's make sure we all understand. The magnitude of F is 1.2 kilonewtons. We know that. So the magnitude, I actually didn't make it this way, the magnitude of FAB, the magnitude of FAB is given to us as 1.2 kilonewtons. But we need to multiply that now by a directional vector. And to me, the easy way to get the directional vector is to do a little mathematical step here in which we're going to articulate the physical dimensions of the line of action, of that force, right? And this is why we've been harping on since the beginning of the course that the line of action goes forever anyway. We can define a line of action if we know it's somewhere, right? In this case here, the way that we're going to do that is we're going to take the x values of the end point of the line of action, or some defined end point, minus an originating point. So end minus origin. So let me show you what I mean by that. Let's say that since the force is pointing this way, and this is why we went to lengths to, to understand which direction it was going. Force is going this way. That means the origin is up here, the end point's towards the end of the arrowhead, and that can extend as long as we want it to be. Let's imagine that the end point was right down here, at point B, I think it is. Yeah, point B, and the origin is up here. So now, if I buy into this end minus origin story, then the x value of the end point, the x value down here, would be this distance from the y-axis over to here, which is not overly obvious, but that's the same as the 1.6 meters we have here. So I got 1.6 meters to get here, plus another 0.8 meters to get here. So my end point is 2.4, and then my origin point is the x value for this piece right here, which if we come from this right here, that x value is 1.6. So 2.4 minus 1.6, and that's going to be the x component. In fact, you know what I'm going to do? Since we're going to eventually make this into a unit vector, let's put that in unit vector notation, even though it's not quite unit vector there yet. We're going to make it unit vector. So now to this, we're going to add the differences in the y values of the endpoint minus the origin. So in this case, the endpoint y value we see right here, positive 1.5. The origin, which is sitting right on the xz plane, is 0. So this is simple. This is 1.5 minus 0 right here. And that's going to be in the unit vector j direction when we're done with it. And then to that, we'll add now the changes in z. So check it out. The value of z down here at the endpoint, since this is right on the xy plane, the value of z down here is 0, right? So I'll have 0 for the endpoint minus the value of z at the origin point, which the origin point is up here at positive 2, according to that dimension right there. So 0 minus 2, now that one in the unit vector k direction when we get done making it into a unit vector. So how do we make this into a unit vector? Well, first of all, let's extend this just a little more. Let's put some numbers on this. So right now, 1.2 kilonewtons here times, what do we have here? 2.4 minus 1.6 is 0.8. So 0.8 I plus 1.5 J minus 2K, and I said I need to make that a unit vector. The way we do that is we're going to divide these numbers by their overall magnitude. And remember, the magnitude is given by the square root of the sum of the values. So that down here is going to be the square root of 0.8 squared plus 1.5 squared minus, or let's say plus minus 2 squared. When I do that, we're going to get, let me just write this whole thing out here now. We're going to end up with the following. We're going to have 1.2 kilonewtons times the following. We've got our magnitude of the force multiplied by these terms right here, which comprise a unit vector. The reason I know that's a unit vector, by the way, folks, is if I looked at the magnitude of these. In other words, if I squared this, and I add to that the square of that, and I add to that the square of this, and I took the square root of that, I'm going to have 1. So the magnitude of that, those three pieces right there, are my unit vector magnitudes. It's also worth remembering that each of these are the directional cosines. So if I want to know what the angle was with respect, or between that force and the x-axis, it's the inverse cosine of 0.305. Between it and the y-axis, inverse cosine of 0.571. We don't need to worry about that. That's not the purpose of this. It's just kind of a little bit of an FYI. So now, what I can also do, because remember, I'm still aiming to solve the moment, I need the components of the force. I need to put the components of the force into my matrix when I do the determinant. So I can go ahead and multiply this out. So 0.305 times 1,200. Let's see what that looks like. That means my force vector, my FAB vector, the thing I wanted in the first place, 1.2 times 0.305, that ends up being 366 in the unit vector I direction. 1,200 times 0.71, so plus 685.2 in the unit vector J direction. And then minus here, so minus 0.762 times 1,200, that gets us to minus 914.4, and that's in the unit vector K direction. So folks, importantly, right there is our completed, I guess is the better way to say it. That is our completed force vector right there for our purposes of figuring out this magnitude of the moment. So let's take this a step further. Let's remind ourselves that the moment then, again, R cross F, that's going to be the determinant of the 3x3 matrix, in which the first row is always just going to be IJK. The second row is going to be the R, the parameters of the directional vector R. We haven't even done that yet. But the third row is going to be the values for the force vector, which we got that now, so we can plug those on in. So the third row here is going to be 366, 685.2, minus 914.4. So got those. And then the only thing that remains now, folks, is we just need to come up with the directional vector R. And let's remind ourselves what that means. The directional vector R is literally any vector that goes from our moment center, the place where we're trying to figure out the moment about O, so our moment center is right here, that goes from the moment center to literally any place on the line of action of our force. And it can be any. place. I can't hammer that point home far more than that. So why don't we pick a place? Let's arbitrarily just say, all right, how about we use A up here? A is a pretty obvious place in terms of where it's at. So if I want to go from point O up to A, I'm going to draw that in here, folks. This is probably lightly, but point O up to A is a line that looks like what I'm doing right here. This is going to be my R vector. To get there, look at it and ask yourself, if you had to go a certain amount in the I direction, plus a certain amount in the J direction, plus a certain amount in the K direction, how would you get here? Well, we see that we'd have to go this distance right here in the X direction, and then come up this distance in the Z direction. So that means that the R vector associated with this would look like the following. It would be, well, that distance here would be 1.6, in line with that, 1.6 in the I direction. I'm going to write it over here. R is equal to 1.6 I. Worth noting that this point here and this point here are both on the XZ plane, so they don't go anywhere in the Y direction. All right, they're both on that plane, so therefore plus 0 J. So 1.6 I plus, in this case, going in plus direction, this distance right here, which is 2J, or 2K, so plus 2K. And that right there is a perfectly legit R vector. So now, again, not the only one, but it's a perfectly legitimate one. So if I come over here now to my moment, plug those terms in, I'm going to have 1.6 for I, 0 for J, and 2 for K. And right there, folks, we've essentially done the problem. The only thing that remains for us now is we just need to do that determinant. I'm going to go through it fairly quickly, folks, because it just doesn't, I don't think it benefits a whole lot to dwell on the math here. Give me time to write this up. So as we know, the determinant would be calculated by the following. We're going to alternate, so we'll start with plus. So for the I component, we're covering up the I column, we're covering up the I row. So I'm going to have 0 times minus 914.4 minus 2 times 366. And that's going to be my value in the I direction. I started with a positive. Yeah, fire away.
You were covering up the I column, so there shouldn't be 266, right?
Yeah, you're 100% right on that. I totally blanked. So I'm covering up over here. So it's not 366. It's 685.2. Thanks for catching that. So again, covering up this, we're left with a 2 in the 685.2. So 685.2. That is the quantity in the I direction. And again, thank you for the catch. So we started with positive, now we're going to alternate. So we're going to go to negative next. Now it's going to come the J direction. So now we're going to cover up this column right here. We're going to be left with the 1.6366, the 2, and the 914.4. So start things off with 1.6 minus times minus 914.4. Subtract from that 2 times 366. And that is going to be, whatever that works out to be, that's going to be our value in the J direction. We'll alternate one more time. So plus minus, now plus again. This time we're covering up this column right here. So we're left with 1.6 times 685.2. Minus 0 times 366, so that's obviously 0, but write it out anyway. And that's going to be in the unit vector K direction. And folks, when we do all the math on that, you're going to come out with the following. It's going to end up being that your moment vector is going to be minus 1370.4 in the I direction, plus 2195.0 in the J direction, and plus 1096.3 in the unit vector k direction. The only thing we have to add to that, folks, is that when we go back to the original problem statement, the problem statement asks us to calculate, hear this, calculate the magnitude of the moment. So what we have right now is we got the moment vector. To get the magnitude of the moment, then we're just going to take those three terms, square them, and do the square root. So the square root of minus 1370.4 squared plus 2195 squared plus, what is that last one, 1096.3 squared. If we plug that all in, folks, and crank that out, you're going to find out that the final magnitude of this ends up being 2,810, or about 2.81 kilonewton meters, and that one right there finally solves that problem. So first questions on that, anybody? Questions on how we got there? Fire away.
So when we finally found the projection of R, why
Yeah.
did we not divide it by everything squared?
Oh, great question. Oh man, I'm so glad you asked that question. I'm gonna repeat it because I want everybody to hear it, right? So your question was, when we found the directional vector R, why didn't we divide, because the whole purpose of dividing by the magnitude is to convert it to a unit vector. So its functional length would be 1, right? And we don't want that because R is actually a moment arm, right? So it really does need to be representative of actual distances, not normalized to be a unit vector. So we didn't do that. So we didn't want to do that.
So why did we want the force in the unit vector?
So the force is a different story. What we were doing with the force, and I've erased it all right now, but what we're trying to do with the force is we're trying to create a force vector that specifies how much of that force projects into the x-axis, how much projects to y, how much projects into z, right? The methodology there was to take the entirety of the force magnitude, the 1.2 kilonewtons, identify a unit vector so we had the directionality of it. All we wanted was directionality. Then I multiply those directional components by the force magnitude and I get the how much in each direction. So totally different animal in that case. But good questions, because buried in your question is something important, folks. Buried in that question is, at the end of the day, we are taking ultimately the magnitudes of the force multiplied by the magnitudes of the moment arm to get the moment. So force times distance, nothing changed in that regard. Did that take care of you?
Yeah.
Okay, good. What are the questions? Yeah, fire away.
What was the prompt again? What was the exact wording of the question?
The exact wording of the question on this one went like this. It's 2 sentences. The turnbuckle is tightened until the tension cable is 1.2 kilonewtons. The ask was to calculate the magnitude of the moment, about 0.0, due to the force acting on point A. What other questions you guys got? Yeah, fire away.
So why do we care about it as a three-dimensional vector and not just as a rotational force around, like in a 2D sense?
Run that by me again.
Why do we care about the three-dimensional vector that we just got instead of just, I guess if you were to look at it from a top-down, that counterclockwise rotational way?
I think this is the answer to your question, although I'm not crystal clear. When we were in 2D world, everything, all the forces were, by their nature, drawn on a plane, right? There was no projection in or out, but they exist on a plane, which means when they exist on a plane, they only cause rotation about one axis. But in 3D world, they cause rotation about multiple axes. In fact, we're going to see that shortly in that problem over there. So I might come back to this when we get to that one over there because it's a great question. But I think the answer to your question is when we got done figuring out this moment, we had a vector representation. What's in that vector representation is, this is literally telling us, this is the magnitude of the moment about the x-axis.
Yeah.
This is the magnitude about the y-axis. This is the magnitude about the z-axis. So in 2D world, we always just had one axis and one answer. In 3D world, we automatically are going to have three answers. In other words, how much am I rotating about, in this case here, my x-axis? How much am I rotating about my y-axis, and how much is that causing rotation about the z-axis?
Okay.
Does that help?
Yeah, I guess I should imagine that 0.0 is on like a swiveling ball rather than just a swiveling arm.
That's how you way to think of it, yeah. If you want to think of it that way, or again, in fact, that's a real fair way to think about it, right? Another way would think of, okay, I got 3 iron rods here. I got an iron rod representing that, an iron rod representing an iron rod, and they're all welded together right here. And now, because of that, you can say, okay, if I could instrument these rods and measure how much torsion I'm getting on the rods, then the amount of torsion I would get is what I expect over here. The amount of torsion on that one, you know. So that's another way to see it. That's a great way to see it. In fact, I'll take yours even a step further, all right? There is a methodology in this in which right now we define 3 axes that pass through point O, right? There's also a methodology in which we could define an arbitrary vector line that passes through that and project the moments on that arbitrary line. Trust me, I'm doing you a favor by not doing that, the math on that. But there's scenarios where you might need to know that. Like, yeah, what's the moment about some arbitrary axis? It's doable, it's figurable. Did that take care of you though? I want to make sure it took care of you.
Yeah, it did.
Okay, cool. Good question. These are great questions, folks. What other questions might you have? Anybody, anything at all on this particular problem? Okay, let's put this one to bed. Now we'll go over to this one. Finally, and the last thing that we're going to see here is a 3D equilibrium problem. Folks, remember that we've already talked about 3D equilibrium in the sense that unlike 2D equilibrium, where all we needed to do to assure equilibrium in 2 dimensions was we had to show that the sum of the forces in the x direction, the sum of the forces in the y direction, and the sum of the moments about some point was 0. That's all we needed to do. In 3D world, it's really not that much more, but it's an extension of that, in that in 3D world, we have to be able to show for equilibrium, we have to be able to show that the sum of the forces in the x direction add up to 0, the sum of the forces in the y direction add up to 0, and now we have sum of the forces in the z direction, and they're going to add up to 0. And to the question we just walked through, we also need to show in 3D world that whatever moments I've got about an x-axis, they add up to 0. Whatever moments I got about a y-axis, they add up to 0. Probably switching my axes here, right? And whatever moments I got about the z-axis, they add up to 0. There are 6 requirements in 3D world, 6 requirements to show equilibrium. In 2D world, there are only 3. This is all we got to do, though. But to do that, and before we even do a takeaway of what I wanted to show you here, to do that, there it is. I was looking at my notes, I'm like, yeah, where's my notes? I think I've dropped some notes here somewhere. Yep, there we go, we're good. To do that, we got to rely on 2 things. Number 1, get ready for the shock of the semester right here. It all starts with a free body diagram. And number 2, we're going to apply equations of equilibrium. The only difference now is we're going to find that the equations of equilibrium get easier when we do vector math. That's literally it. So check out the problem we've got up here, folks. This one is one of the ones in the book. It's problem 362 in newer versions of the book, in case you might be wondering. It goes like this. So check this out. I'm going to read you the narrative, but focusing on the picture we got right here. Hear this word? The uniform I-beam has a mass of 60 kilograms per meter of its length. So 60 kilograms per meter of length of the I-beam right here. Determine the tension in the 2 supporting cables and the reaction at D. So check this out. We've got this I-beam. We're told again, what was that? It was, what did they say, 60? Yeah, 60 kilograms per meter. So for every meter of this thing, we've got 60 kilograms of mass. Look, let's do the quick math here. 2, 5, 1 more, 8. So we're going to have 8 meters of this thing, so 8 times 60, 480 kilograms of mass total. But check it out. It's resting on this triangular shaped or kind of prismatic shaped element right here, resting on point D. So hard to see it, very hard to draw these things in 3D, but imagine that's a triangular shaped thing. The beam is simply resting on that. So it's just resting on a point, a line up there. And let me remind you we're in chapter 3 right now, right? We're in chapter 3, meaning that even though it doesn't say anything about surfaces, unless we're told there's friction, they're smooth, right? These are smooth surfaces. That's a very important thing here. We're 3 chapters away from friction at this point. So whatever this looks like here on D, whatever that looks like, that is a smooth surface. We need to remember that. So I'm holding up the I-beam with this prismatic shape down here, and then I've got these 2 cables. There's a cable right here, a cable right here, point A here, point B, point C. We got these 2 cables. The ask of this problem is, again, figure out the tension in the 2 cables and that reaction at D. So to do that, we need to create a free body diagram. And folks, I'm sure you'll understand when I tell you it's not going to get any better if I redraw this thing. So let's do a free body diagram. We'll kind of take the cheap, easy way out on this one right here. So if I think about these cables here, if I separate the cable, I'm going to have a tension in this cable right here. I'm going to call this one, since this is cable AB, I'm going to call this one tension AB, so TAB. And yeah, that's going to be a vector quantity. If I break away this cable right here, then I would have a tension in that cable right here. So here's my tension in cable AC. And again, I'm going to keep the, I just want to keep all the dimensions up there. It's just going to make it so much easier if we keep those dimensions up there, folks. And then down here at D, here's where we got to think about this one, folks. Down here at D, we just got through saying that this is a smooth surface. And we got to remember, what have we been saying all throughout the entire course when it comes to how do we represent forces when we're not certain? When we're not certain, we apply the test. We apply the test of would I face resistance to motion in any of my axial directions. So for example, if I define, and we need to do this anyway, so let's go ahead and do this. Let's go ahead and define our XYZ axis right through point A. And you'll see why I'm going to do that in a second. So I'm going to run an axis here. I want to let my x-axis come out the middle here. So here's my x-axis. I'm going to have my y-axis coming over like this. So here's my y-axis. And I'm going to let my z-axis go right up the middle down here, up here, folks. So there's my z-axis like that. So now, with that axis defined, go back and just think about this. Using that concept we just talked about of if there's no resistance to motion, there can't be a force. If this is a smooth surface here, and the interface is smooth, if I try to move this beam in the x direction, would I face any resistance to motion? No. So there can't be an x force. If I took this force and tried to, not this force, this beam, and tried to move it along the y direction, would I face any resistance to motion if I tried to slide that along the y direction there on that smooth surface? No. So no force. If I took the beam and tried to shove it through this thing in the z direction, would I face resistance to motion? Yep. So therefore there's a force there. So in my free body diagram, I need to, and I'm going to get rid of this because remember we've always said free bodies, we need to draw it isolated. I'm kind of doing that here, but not perfectly. But I'm going to draw now a force coming up, which is representing the only force I've got here, and it's coming in here and applying itself on the inside. I'm going to call this force D. So that's the force that represents the reaction or the resistance to me trying to push this beam through that prismatic shape that's no longer there. And then folks, the only other thing I've got here is we were told this is a uniform beam. We know that it has an overall length here of 8 meters, 2, 5, and 1 more meter up here. We know we're going to be calculating a weight. We know the weight is going to point straight down towards the center of the earth, and it's going to emanate here in the geometric center of this, so the weight's going to come down like this. Let's get that weight figured out. First things first. So we're told that this thing has a mass of 60 kilograms per meter, and it's 8 meters long, so the overall mass therefore is going to be 60 times 8, which is going to be 480 kilograms. And just like always, we know that that's not a force. We know we got to multiply that by 9.81 to make it a weight. So the weight is therefore gonna be 480 kilograms times 9.81 meters per second squared. That's gonna make it into newtons, and that's gonna end up being 4,708.8. So 4708.8 newtons. Now we know what the weight of this is. So let's come over here, and I'm gonna extend this just a little bit, folks. I don't want to confuse it with that 5 that's sitting right there. So I'm gonna let my weight come down here, and 4708.8 newtons. All right. So now we got that in. So now if you just take a moment and look at the result of that, as it stands right now, we have got a free body diagram which is showing, like all of our free body diagrams do. Just want to make sure we're on the same page here. The free body diagram shows the isolated thing that we did the free body diagram of. It shows a coordinate axis system. It shows weight when we know it. And we're also showing forces where we used to be connected to something. So used to be connected to these cables up here, got force there, and I used to be in contact with the prism at point D. I got a force there. So this is like any other free body diagram. Same old, nothing's new here. But now with that in mind, we know that we're going to do the equations of equilibrium, do the moments using vector notation, right? So that means we've got to convert some forces into their vector equivalents. I'd like to start with force TAB right here. So if I look at force TAB, and I want to look at that in vector notation, then folks, just like we saw in the previous problem, a way that I can do that is I can write the force vector as being its magnitude, which I don't know its magnitude right now, but I'm just going to call the magnitude TAB. Its magnitude multiplied by a directional vector. So in this case here, I need to create that directional vector using the same methodology I did just a moment ago. Whereas we look at TAB right here, and folks, in this you're going to see the reason I put the origin right here at this is going to force my my originating point on these two vectors right here to be 0, 0, 0, right? So 0, 0, 0 here at the origin. So when I think about the x directionality of the endpoint, so the endpoint of this arrow is right here, but that was right in the YZ plane. It's not moving anywhere in the x direction. So endpoint is 0x, origin 0x. So that means my first term up here is going to be 0 minus 0, and that's going to be the I direction. Now for the Y direction, if you look at this one carefully, positive Y is going this way, but this terminates up here in the negative direction, and that's 2 away from the Z axis. So that place right there is -2 in the Y direction. So -2, 0 here. So I'm going to have then plus -2 minus 0 in the J direction. And then as far as the Z direction goes, endpoint here is at Z is equal to 3. Origin is where Z is equal to 0. And that doesn't become a unit vector until I divide by the magnitude. So the square root in this case, 0 squared, we all know is 0. But here I'm going to have -2 minus 0, which is -2. So -2 squared plus 3 squared here. And folks, when I get that done, I'm going to have the following. I'm going to have that my vector TAB is going to be equal to my magnitude TAB times the following: 0I minus 0.555J plus 0.832K. And folks, I'll guarantee you that what you have here, if you did the magnitude thing on that, you'll find that is in fact a unit vector. So we got one of them done. Let's do the exact same thing right now for TAC, although this one we can move a little bit quicker on, folks. So vector for TAC is going to be the magnitude of TAC times, now we'll do the same thing here. For the exact same reasons, the x value is going to be 0 in this case because TAC comes up here, it's entirely in the YZ plane. So 0x minus 0x again in the I direction, plus now, and this is really the only place this is going to change. Notice that the endpoint for this one is actually in the positive y direction. This is tending towards positive y. So the y value for the endpoint's positive 2, the origin's 0, so now that's going to be a plus 2 minus 0. And again, this is the only difference. The previous one was in the negative 2 direction. This one's in the positive 2 direction. That's the difference we're seeing right here. And then we got the same thing here on the for the z direction here. So the endpoints at z is equal to 3, origin 0, so plus 3 minus 0 in the k direction. And we need to divide all this by the same magnitudes. So minus 2 squared plus 3 squared. And folks, when we're done with that, in fact, I think I'm going to write these all up over here just to keep the board space. This is clearly going to have the same terms in here. The difference is going to be that's going to become a plus. So TAB is equal then to magnitude TAB times 0I minus 0.555J plus 0.832K. And then TAC, coming from right here, is going to be magnitude TAC times 0I plus 0.555J plus 0.832K. And all of that fell out from what we just did in determining these vectors right here. Everybody good with that? No questions on that? Okay. Now, similarly, folks, I'm going to come back and do the D vector later. We'll get to that shortly. But let's just note here, folks, we do know actually we can do the D vector right now. So the D vector, I'll just write this and then we'll see for sure why it is what it is. So in the case of the D vector, D is a purely Z directional force, right? It's straight up and down on the Z axis, it's going in positive Z. So that's going to be the magnitude of D times 0I plus 0J plus 1K. Similarly, the weight vector is going to be the magnitude of the weight, which in this case we already know the magnitude at 4708.8, so 4708.8, and that is a purely Z directional force, so 0I plus 0J minus 1K in this case here. Or in other words, more simply put, folks, this is going to be equal to nothing more than D in the unit vector K direction, and this is going to be equal to minus 4708.8 in the unit vector K direction. So with that said and done, we now have all of the forces in our 3-by diagram memorialized over there, far side of the whiteboard, as purely vector notation forces. But now to the solution. So if you think about this, folks, we know that the sum of the forces in the x direction have to add up to 0. We know the sum of the forces in the y direction have to add up to 0. Some of the forces in the z direction add up to 0. We're going to put some numbers on these, and I just want to give you a preview. When we have figured out what the value of D is, the value of TAC, and what the value of TAB is, we're going to be able to multiply it through by all those terms right there, right? So we're going to have a certain amount in the x direction for all these. We're going to add those pieces up. They got to add up to 0. A certain amount in the j direction, add those pieces up. They're going to add to 0. Same thing going on over there for the k direction. But I want to come back to that later. We got to figure out some unknowns. So the way we're going to do that is we're going to go ahead and do moment equations. And what I propose we do, because remember, throughout our entirety of the work that we did in 2D, we always sought to write moment equations about points where we could make forces go away. And we said, we can do moments anywhere we want. It's all the same thing. Everyone's legit, but other ones make it a little bit easier than some other ones might be. Guess what's happening in 3D? Nothing new, it's the same thing. We can take moments anywhere we want, but some places might be smarter than others. So think about this. If I did my moments about the origin right here, about point A right there, then I take that out of the moment equation, I take that out of the moment equation, and now I got moment equations that only contemplate the weight and force D over here. So let's do that. Yeah, fire away.
How did you figure out where the weight was supposed to be?
How did I figure it out?
Yeah.
Are you asking me how I got this number?
No, like the position it's at.
Oh, sure, no problem. The problem statement told us that the beam was uniform, right? So if it's uniform, geometrically consistent, therefore if this is 8 long, then this distance here, and I didn't write that up, it's probably worth doing that, but this distance here to the weight is 4. So if it's 8, it's half of that, because of the uniformity. Okay?
And you said it's -1 because it's down right.
This one here, yeah, because it's going in the negative. It's
Negative, yeah, that's one case negative.
Yeah, the magnitude is always positive. The directionality in this case would be a negative z direction.
Okay, and if it was -1 because the beam's too high, it's the middle of the beam.
It's all directionality in that case. You have positive for positive coordinate. I'm sorry, positive for positive axial direction, negative for negative direction. Good questions. All right, so now we've decided we're going to do the moments about the about point A. So just like any other, I want you to think about this. What I'm about to write here, this is going to look just like any other sum of the moments equation, except we're going to have vector notation. So I want to sum my moments about A. Do note here, folks, that we already saw this with the example of R cross F we saw last Thursday. I don't need to worry about this counterclockwise convention thing because the math's going to fix it all for me, right? So for the very first time in the course, you're seeing me write a sum of the moments equation without the counterclockwise symbology. We're letting the math take care of it for us. So that's going to be equal to the R, well, all of our moments are R cross F, right? So I need to have a R vector that's going to go from this point over to the weight vector. And then I'm going to cross that with a weight vector. So let's write this as R for the distance from, since the origin's A, let's call that A over to the weight W. So RAW crossed with, in this case now, that's going to be crossed with the weight vector. So that's going to take care of the moment due to the weight about point A. I'm also going to have a moment due to D over here. So in that case, I'm going to add to this I shouldn't say a legitimate R vector that goes from A over to this line of action. If you think about that, this can just be some vector from A over to the line of action of D. We'll call it that. We'll see what that is in just a moment, by the way. So R from A to D crossed with the D vector. And then as far as those R values go, the one from A to the line of action, remember the line of action going forever in both directions. I just need to go from here to that line of action, any place on the line of action. And I've already asserted that this is at 4, so here this is 2 from the end, and the line of action passes through 4 from the end. So that means I need to go in this direction here, a total of 2 units. But I'm going in the negative I direction. This is positive I here, negative that way. So minus, let me write this out. So the R vector from A to W is I need to go -2 in the I direction. I need to go nowhere in the Y direction, nowhere in the Z direction, so simply plus 0J plus 0K, and that takes care of that one. And then my R vector to go from A to D, again, I want to travel from point A to the line of action of D back here, so I'm going to go in the negative I direction. The distance in this case would be, what have we got here? So this would be 6 to the end, but I'm going to come back 1 because of that. So 6 minus 1 is 5, so I'm going to go -5 in the I direction, and in the same sense as before, I need to go nowhere in the J direction, nowhere in the K direction. So plus 0J, plus 0K, and just like that, now I've got those vectors. So now, with all that said, let's plug in the determinants here, folks. So for RAW, we've already asserted that we're going to use negative 2, 0, 0. So minus 2, 0, 0. And then that's going to be crossed with the weight vector, which we've got from way over there. So that's going to be 0I, 0J, and we said minus 4708K. So minus 4708.8 right there. And that's going to take care of that determinant. I'm going to come back and fill in some stuff later. I'm going to add to this now the next determinant. So RAD, we've already asserted over there. So I, J, K, that's our first row. It's always our first row, as we already know. The R vector minus 5, 0, 0. And then finally, from over here, the D vector, 0, 0, and the unknown force D. That's important, what I just did right there, folks. We just put an unknown force in there because remember, one of our objectives is to figure out what that unknown force is, so we just put the unknown force D in there. Okay, so now, I am going to spare us having to see all the math to work this out. I'm just going to tell you it comes down to the following. This determinant is going to work out to be 0I minus 9417.6J plus 0K. And then to that, I'm going to add the determinant here, which comes out to be 0I yes, plus 5 times D plus 5D in the J direction plus 0 in the K direction. So, very importantly, these are the terms that fall out of working the determinant, all right? That's what we got from the determinant. Now, if I sum up all my individual components, this is the important part. If I sum my moments in the x direction, because I know for equilibrium, my sum of my moments in the x direction has to be equal to 0. In this case here, I'm just going to take the like components, the like I components. This is where the math gets pretty. 0I plus 0I equals 0. That simply tells me I have no moment about the x-axis. And folks, before we go any further, let's go back and look at that. Does that align with what we expected? So if you think about this, to have a moment about the x-axis, we'd have to have forces that are causing this thing to twist along the x-axis right here. This force passes through the x-axis, it's not going to cause any twist. This force is passing through the x-axis, it's not causing any twist. This one passes through the x-axis, and so does that one. None of these forces were ever going to cause this beam to twist in the x-axis, and our math just showed us that. Now, for what it's worth, folks, we should look at this and also realize none of these forces are going to cause any twist about the z-axis either. If you look at this force here is going to cause rotation about the y-axis. This force is going to cause rotation about the y-axis, but they don't cause any twist about the z-axis. We'll see that in a minute. But let's go ahead and sum up the y forces now. So if I sum my moments in the y direction, I'm going to have the following. I'm going to have minus 9417.6 plus 5d, and that's equal to 0. Well, folks, check that out. Looks to me like I can solve for d right there from that one equation. If I do that, I'm going to find that solving now for d gives me that d is equal to 1,883.5 newtons. So just like before, now I have the ability to know what that force is. And then lastly, as I said a moment ago, if I now sum my moments about Z, I'm simply going to have 0 plus 0 equals 0. And once again, we see that we would not have had any moment about the Z-axis. So in the context of what we're trying to do here, folks, think about this. In the context of what we're trying to do, we had to show equilibrium, we had to show that the sum of the forces in the x direction, y direction, and z direction were all 0, and that the sum of the moments in around the x-axis, around the y-axis, around the z-axis, that those were all 0 as well. 3 of these things are now done. We've done the moments about 0, we've got that. This, by the way, becomes a 0 moment when d is equal to 1883.5. All that remains for us now, folks, is we just need to sum the forces in x, y, and z. Pause for 2 seconds though. Are we good with what we've seen here? I know it's a lot of math, trust me, I know that. You just need to see that, yep, there's some pattern here. Okay, good. Now lastly, we sum forces. And folks, check this out. I'm now going to sum my forces, but I'm going to make my vector, I'm going to make the sum of the forces a purely vector thing. So I want to sum my force vectors, which means the sum of vector TAB plus vector TAC plus vector D plus vector W. The only way that I'm going to have equilibrium is if the sum of all those force vectors is 0. So I'm going to set that equal to 0. But what that means is I can now sum the individual components. I'm going to write this all out. So right now, the TAB is the following. So I'm going to multiply TAB through all these things. You're going to see why in just a minute. So I'm going to have, I'll have 0I and I'm simply going to stop with this one, folks, because I just want to make sure we all see that what I did here is I multiplied through TAB times 0, simply 0 in the I direction. TAB times negative 0.555 gives me negative 0.55 TAB in the J direction, and then 0.832 in the K direction is 0.832 TAB in the K direction. So I want to show those things. I'm going to do the same thing now down here, so plus another 0I. This time now plus 0.55 times TAC, so plus 0.555 TAC in the J direction, plus 0.832 TAC in the K direction right there, folks. So now these next 3 terms, IJK, coming from these terms here, I'm going to keep the process going. So from there, I'm going to add this. So I'm going to add now another 0I, another 0J, but a plus D here in the K direction. But importantly, we've already figured out what D is, right? We already know it's 1883.5, so plus 1883.5 in the K direction, and that takes care of the unit vector, or the vector for D. And then our final one is going to happen right here, so we're going to have another 4708 times 0, so plus 0I plus 0J, and then lastly minus 4708.8 in the K direction. One very, very long equation. But here's how it all comes in for a landing. All we need to know now, or all we need to think about, is just like it was when we had 2D statics. We summed up the force in the x direction, and those had to add up to 0, right? So if I take the x components of all these, the x components of each and every one of these are the I vectors. So if I sum forces in x, looking at this from a magnitude standpoint now, I'm going to have 0 plus 0 plus 0 plus 0. So the sum of the forces in x equals 0. And folks, go back and look at the original diagram. This force here had no x component. This force had no x component. This had no x component. That one had no x component. We never had any forces in the x direction. We just proved it. Now if I sum forces in the y direction, I'm going to have the following. So all my j's, minus 0.555 TAB plus 0.555 TAC plus 0 plus 0. So I'm going to put those in. And this has to be equal to 0. Now folks, no different than what it was with 2D stags. That's just a plain old algebra equation. And as we look at this, it should be very obvious that if I move this to the other side of the equal sign, the 555s are going to cancel out. And a result of this is that the tension in cable AB is going to be the same as the tension in cable AC. That equation shows us that. But honestly, if we go back and think about this long before we let the math show that to us, we had symmetry here, right? This cable was symmetric to this cable right here along that the ZY plane, right? So it's no surprise whatsoever that the forces are equal in these cables. Symmetry told us that. Now the last thing I need to do is sum forces in the Z direction. And if we look at the Z components, I'm going to have 0.832 TAB plus 0.832 TAC plus 1883.5 minus 4708.8, and those four terms, the Z terms here, they have to add up to 0. Continuing to work that out, folks. Let's remember that TAB and TAC are the same, so I'll just convert one of these over. I'll just make this TAB. And folks, when I do the math on that, plug it all in, crank it all out, we're going to end up with the following. The TAB, which we know is the same as TAC, ends up being 1,698 newtons, and we just solved the 3D problem. The takeaway on this one, folks, again, even though, and this is what I want to leave you with, even though the math on this got busier, notice I didn't say harder, I said busier, because of the 3D, the vectorial nature of it. And trust me when I say, I would have no expectation that after seeing it one time, they're always like, oh, I totally get it. If you do, you're amazing. I didn't get it for a long time. But what we see in here is even though that math is a little bit busier, right? The fundamentals stayed the same. The fundamentals were sound. The fundamentals that we had here were, it still started with a free body diagram. We still made the free body diagram the exact same way. We still had to sum the moments, and they all had to add up to 0. We still had to sum the forces, and they all had to add up to 0. The only thing we did different here was we used vector math to make our job easier. That was literally it. And that's the intent. That's the entirety of the whole thing, folks. Anything that we've done so far in stags throughout the entire course and working through chapters 1 through 6, where we focus ourselves on 2D statics throughout, anything you've seen has an analog in 3D statics. We've seen that analog for moments, for example, is a vector process. We've seen the analog for equilibrium, vector process. But the fundamentals don't change. As you finish this course here, remember that throughout this course, we hopefully dedicate ourselves to the idea that if we get really good at making models, in our case the model is the free body diagram, that the math will always come. And I said in the early part of this course, you'll move on now to a second mechanics course where in many of those cases in that second mechanics course, the math for figuring out certain things like stresses and all that will be remarkably easy. The difficulty will be, can you correctly specify the forces? If what you take away from this course was, I know how to create a visual model and apply equations of equilibrium to get me the forces, that next course is going to be way easier. That's the goal here, folks. And by the way, that won't be the end of it. For you mechanical engineers specifically, for you mechanical engineers, there's going to be a course in machine design coming up. I want to take a wild stab at what you're going to be doing in that. Free body diagramming, solving things. You can apply it to a lot of different things you're going to study in mechanical engineering and even beyond. So hopefully that fundamental that I've tried to teach here throughout this course of it's all about drawing pictures, hopefully that shines through. Does anybody have any final questions about this? About the final? Anything at all? Don't forget to stop by and see me, just make sure that I got your name, that we're working together on the midterm if that applies to you. Otherwise, you guys go have a great rest of your semester. Hope finals go well for you, and we'll see you next time around.
What?
Bro, we are.
Blaze your own path.
No,
Not
I just
midterm
want
stuff.
to ask about this.
Okay, I just want to make sure that was the case.
Yeah, sorry. Thank you.
So did you end up getting 3 done? I got 2 done.
That's 3. It was, so he's just fine. It was kind of what he said. Just cross out the word. It's just the sign. Put 1 over sign. 1 over. I don't know. I did number 2 and I was getting confused because I didn't know you can end up putting these 2 forces, the upper force, as 1 force together. And so I ended up just doing a bunch of other stuff.
Yeah, I got that done while he was giving the lecture.
Okay.
You want to meet up like